Hello, everybody. This is Dr. Living Day, and I am a professor in the Industrial Systems Engineering at the University of Regina. First of all, let me extend my very warm welcome to all of you, the students of the University of Regina. Also, thanks to the our student union for organizing such a great event, the Welcome Week 2021. Okay, for the Welcome Week 2021, I was asked to give some talk about my research. I think the interesting topic that involved in my research would be nonlinear dynamics. Okay, let's get started. And I would like to say something about linear and nonlinear systems, solution of nonlinear systems, and the future of nonlinear dynamics. Okay, hopefully that will be interested by you. Let me share my screen with you. Okay, so linear and nonlinear systems. Linear systems are everywhere. We have seen in our physics, mathematics, engineering, and everywhere in the world, actually. But why nonlinear? And what is the significance of nonlinear systems existing in our world, and how we solve the nonlinear systems? And what is the current research, state of research for nonlinear dynamics? Okay, as I said, my name is Liming Day, and a professor in the Industrial Systems Engineering. And this is my contact information. If you are interested in this topic or anything relating to the courses or research that I have, and please contact me. And you can also find my research, my teaching at this website. Okay, linear systems. And as I said, the linear systems are around us everywhere. For example, let's say when we get to high school study, and the high school, we have learned friction. And the friction is just described by friction force equals to the coefficient of friction multiplied by normal force, right? Everybody knows that. This is a typical linear relationship. And that linear relationship has been used for us for studying and for applications as well. However, can we say this linear equation describes the fact of friction completely? Maybe not. Let's say, I'll give you an example. You can do a test at home. Let's say you have a plate and you put a piece of paper on it, and then you raise up one end of the plate and make an angle between your plate and the horizontal surface of your table, for example. And then at a certain angle, your paper will slide down from the surface of the plate. That angle, we call it the friction angle, actually. And then if you fold the paper and make it a small piece and put it in the same plate, and then you may find out your friction angle different. That implies that friction is not just based on the coefficient of friction and normal reaction, but also the contact area. And actually, there are a lot of factors involved in the friction force, such as deformation, such as the moisture such as the condition of, let's say, temperature, deformation of the materials, etc. There are a lot of things, and it can be complex and nonlinear. It's not that linear. So exactly what is nonlinear? Let's say we have another relationship that we know of from high school. And by saying that, let's say I have a spring. The spring force is determined by spring force equal to the coefficient of spring constant or spring stiffness, K, multiplied by the deformation from the end stretched position, right? That's what we have learned. However, that relationship is also linear. And it actually, in reality, especially when the deformation becomes larger, then this formula may probably be more accurate. In comparing with this linear relationship, this one is nonlinear because we have x to the power 3 there, and you can have x to the power 5, etc. Okay, that's the nonlinear relationship, which is more close to reality. So, well, there are a lot of linear relationship among us, among the scientific and the engineering areas, and such as the thermal expansion and the equation of motion, etc. And the fact is that actually our world is nonlinear. Nonlinear relationship, as shown by this equation, would be more close to reality or to the nature. Okay, so let's say what kind of a relationship that we may have between linear system and a nonlinear system. Okay, say this is a pendulum. We call it the simple pendulum because we are saying that we have a rope here with the length L, and we consider that mass is concentrated at this point. So we can consider this point the mass of this point M, and for this situation, we consider this object as a particle. Okay, so that's the simplification and assumption. I say all the mass is concentrated at this point, and the length of the rope will not change during the motion. You see, this one will be oscillating this way, right? Okay, so everybody have seen that, but you may probably have seen some clock like that. Okay, however, if you want to describe this motion accurately or by a mathematical manner, then we may probably need to find out a relationship. That relationship we can use Newton's second law. Newton's second law is F equal to ma. Okay, we all know that. And graphically, we can describe Newton's second law in this manner. Okay, so by Newton's second law, and we're saying that this is, I don't want to bother you by the dynamics. Anyway, we can set up an equation. We call it the equation of motion or governing equation. Theta is the angle. We call it angular displacement, and divided by g. G is the constant of gravitation, the gravitational acceleration, and L again is the length sine theta. Theta is this angle, but this theta with the 2 dots on top indicating the second derivative, or we can say the acceleration of the motion. Okay, so this is an equation that we can use to find the solution which will be used for describing the displacement of the oscillation or the solution of this governing equation. But in this case, for this equation, we call it nonlinear equation because sine theta, well, that will be sine sinusoidal curve there, right? If we have a sine theta there as a function. So it's not linear. So that brings this governing equation nonlinear. And the nonlinear governing equation like this is very difficult to solve, if not impossible. Okay, so what people would do, they would say, okay, well, this is nonlinear, well, I don't like it. Let's make it linear. Then make it linear, that process is called linearization. Okay, then sine theta, we say, wow, when theta is very small, then we can approximately assume that sine theta equal to theta. Okay, and a lot of people accepted that, although that's an approximation. Okay, so then what we do is change the sine theta to theta by assuming that theta is very small. So then we have this one is a linear equation. And the linear equation, we can find the solution, we can find the period of motion, but this is a periodic motion, right? Okay, everything is beautiful, nice. Okay, let's ask a question. Why you want to change the nonlinear system to a linear system? The reason is that nonlinear system is difficult to solve. And then next question would be, you said, okay, sine theta, when theta equal to a small value, then we can say sine theta equal to theta, or approximately equal to theta. So my question would be, how small that theta is, then we can call it small. Is 5 degrees small? Is 6 degrees small? Is 10 degrees small? So that is not certain. In other words, and with another question would be, well, what if the angle is not small? Then the answer is, then if this is too large, the angle is too large, then we don't know how to solve it completely. Okay, so that is the difficult part. So at this stage, we do not, believe it or not, we do not have a very good mathematical way to analytically or completely solving those kind of nonlinear systems. Okay, so that's, so then people will say, wow, what's the difference? Why is the linear and the nonlinear? Would that give us the different response if we have a nonlinear system there, or we have a very large angle of theta there? Yes. So the response of a linear system, typical linear system, is a periodic. Okay, something like that. Periodic. So we can have a solution like what we had previously. You can see that. That's a periodic solution. And in other words, once you give me a value t, I can find the theta, corresponding theta for you. So that implies that we know the response of the system completely. And I can predict what will happen next second, next hour, next day, or next year, right? And everything is predictable. However, if we have a nonlinear system, a nonlinear response can be something like this. That is what we call chaos, chaotic response. Okay, it's not very periodic. Okay, it's in strictly speaking, it's not periodic at all. So that is what we call the periodic, a chaotic response or chaotic phenomenon. Actually, chaotic phenomena has been around us almost everywhere. Let's say, for example, hurricane, we can say the forecasting by saying that, oh, we expect the hurricane will go this direction along this path in the next 4 hours. That is not an accurate prediction. And for longer time, let's say next day, for example, we can hardly predict it because that's non-linearities involved in it. the system, the weather system, is nonlinear. So therefore, well, we need to find how we define those so-called nonlinear phenomena. What are the characteristics of a nonlinear phenomena, especially chaos or chaotic response? So there are a few conclusions that I can give you. By far, the people know that. The first thing is that nonlinear system is hard to predict. Okay, and that's what I have said. Okay, and because we do not have analytical solution, we cannot solve the nonlinear systems completely or analytically. That's the difficult part, and therefore we are not completely we're not understand or comprehend the phenomena or the mechanism of the nonlinear system, unfortunately. Okay. Second thing that I can say, that's a conclusion that everybody agreed in the field, that's the sensitivity of nonlinear system to inertial conditions. So that means a slight change of inertial condition will completely change the response of the system. That kind of characteristic is known now as the butterfly effect. And the butterfly effect, that's just people saying in that way. The flap of butterflies' wings in Brazil set off a tornado in Texas. Okay, that's what the butterfly effect now is widely used everywhere, and especially those politicians like to use it. But one thing that we should understand is butterfly effect is a characteristic existing in nonlinear systems. And it's actually saying that slight change in the inertial condition may probably end a big change of the response of the system. One thing that I want to emphasize here is it doesn't mean that a slight change in the inertial condition will generate a huge energy. The final energy will be changed. No, energy will be the same. Okay, energy cannot be created and or destroyed. Okay, for a given system. So then that's the chaotic system, and and they give us those conclusions. Not predictable and very sensitive to inertial conditions. And there are some other phenomena that we may probably discuss later, or you can find it from the corresponding publications. So what I would like to do is to how we solve those nonlinear systems. Although we can hardly solve them analytically, can we solve them semi-analytically? Or can we solve them numerically with the higher accuracy? That's the part of my research. Let's say, what I do, I would use the piecewise constant argument and make the system as a piecewise linear. Can we make it a piecewise linear system and we solve those systems in a very small time interval? And then we combine them together. If that's so, hopefully we can get a higher, the solution with a higher accuracy. Okay, let's say, what do we do? Let's say this is a typical governing equation, well, the second order differential equation, and the representing the motion, oscillation, vibration of a system. We can do that. Okay, and in some case, we can say, well, this is a piecewise constant argument involved in. Or simply we say, well, we have a system, we have an external excitation piecewise changing. Okay, so that if we can do that, then we may solve this system in the time interval. Okay, you can say, well, there's a hammer hitting the pendulum, or that's probably easy to imagine. Okay, although it's not exactly the same. And then we can say, okay, well, I know the solution for this. if that's a piecewise constant system, a piecewise constant argument, and interpret it as a piecewise constant excitation applying on the system. So then we can solve this equation in this tiny time interval, okay? And then if I have the initial condition, let's say initial displacement and the initial velocity there. If that's so, then well, I can find the solution completely for the system, and over the time horizon that we are expecting. Okay, doesn't matter how large that time horizon is. So then we can solve it. That's an idea. Okay, so now if we have a nonlinear system, then I thought about it and see how can we combine or use a bridge to bridge up those two systems. One is a piecewise linear system, another one is continuous system. Continuous system is mostly widely existing in our world, right? So what I thought was, okay, why don't we have this kind of mathematical description by saying that NT, this was the square bracket representing the greatest integer function. Well, I don't want to bother you about that terminology. You just say that change it to be an integer. Okay, that's an integer over another integer, although this n may not necessarily be an integer. Well, let's assume it's an integer. And then t is time. If we have this, then we can prove this is true. When n approach to infinity, and this relationship is true. So remember, this is an integer, a piecewise constant. Let's say 1, 2, 3, 4, those kind of integers. And then when n approaches to infinity, then we have this relationship. Well, bingo, this is a good relationship. And then actually, we may use this relationship to bridge up the piecewise linear system and the continuous system. Well, that's something that we can take advantage of. So this one has been proved mathematically and in one of my books. Okay, now let's say I have a nonlinear dynamic system. And as I said, this is an typical equation describing vibration or oscillation of a system. Let's say we have G, this function is a nonlinear part of this equation. Well, let's not bother for this time, at this time. And we just describe how we solve this nonlinear governing equation. By, let's say, well, again, in the tiny time interval, I may somehow change this system into this system and get everything in terms of time t. Well, let's say that's what we could do. And the purpose of doing this is in the tiny time interval, we change this nonlinear system into a linear system. Then we may probably can solve this linear system completely inside of the time interval. That's the idea. And then indeed, we can find the solution in this manner. And this a little bit complicated in mathematical format, but it's not that difficult, trust me, okay? And then this G can be a square matrix, or a matrix which is not necessarily symmetric. Well, let's not bother about it, and we can find the solution anyway. We can find the solution in this format. So in other words, the nonlinear system can be solved by this approach. with the piecewise linear system that we managed to write in that form. And here, let's say R is an integer and G is a matrix, actually a matrix to the power of something there, right? And when n tended to be infinity, that power would tend to be infinity. So although this solution is given in this format, it is hard to do the operation. What do we mean by operation? You can hardly do integration. You can hardly do differentiation. Those kind of the operation commonly seen in calculus, which are very useful. Anyway, what solutions is there? And we can say this solution, although it's not a complete analytical solution, we can call it semi-analytical solution. Well, we can solve it. In some case, let's say, if I do not know the solution of a linear system, hey, this is a linear system, and well, in many cases, we can solve it completely. Say, with this linear system, by using the piecewise linear approach that I just described, can we solve this linear system completely or analytically? Let's have a look. So in the tiny time interval, that's what we said, and we can change it in this form, and this t change it to be a constant. This is a constant. I is a constant. N is an integer, right? Then we can solve it in this form. Again, there's a matrix to the power of nt. As I said, n can be infinity. That means we have an infinite number of matrix multiplied. That will be very complex and time consuming, right? If we can find the solution. So we got to do something there. Let's say, assume this, this is a symmetric matrix, right? Symmetric square matrix Q, we write it in that form, and then we find out the eigenvalues of this Q. Do not worry about this. What eigenvalue is a character, describe the characteristic of the system. Anyway, with some mathematical change, we can find it in this format. Okay, Q can be written as E d E minus 1. Actually, this D is a matrix with the eigenvalues in the diagonal line. Okay, and then what is E? E is corresponding to the eigenvalue. This is the eigenvector. And e to the power of -1 is the inverse of the eigenvector. And those are just mathematical change, and then we can easily do that if you are familiar with the matrix. And if that's so, this troublemaking nt, the power, can be moved to inside. Hey, as you can see that. So then we do not worry about the infinite number of matrix multiplied together. So that's the beauty of this kind of operation. And then I found that there's something interesting. And if you are interested in this, and you may probably find that this is interesting too, because this is nothing. And we can rewrite it into so-called Euler's equation. That's the most beautiful equation that people are saying in the world. I don't know why it ends up with this kind of description, mathematical description. However, but it's describing the oscillation, oscillation and the vibration of the system. And what we needed to further saying the physical background of this kind of description. Anyway, when n approaches to infinity, we have a lot of interesting results generated. Yeah, so then let's get back to our original problem. We solve the linear system completely and analytically. Yes, when we let n approach to infinity, we can prove that the piecewise linear system tended to be the continuous system, the solution. That's what we were expecting, and that means we can use the piecewise linear approach to find some of the linear solutions for linear systems through the approach that we just described. And this is a completely new approach. We can find the same solution, which is good. That made me think, well, why don't we use this method to solve nonlinear system analytically and completely? Unfortunately, I am not successful yet. And I have a team of students working on that. And we're still trying very hard, striving to get a solution. We're working on it. Okay. However, although the analytical solution is very difficult to find, but numerical solution can be found without too much of the difficulties, because we have so many of the numerical methods to solve for those nonlinear systems. One of them, which is probably the most popular numerical method, is so-called Runge-Kutta method, and that's an extension of a Taylor series. Very popular, and if you are familiar with MATLAB, and you can find the Runge-Kutta method. Okay. However, if we use the approach, the piecewise linear approach that we discussed previously, and combining with the Taylor series, we may probably get a better solution. So how we do that? Let's say a simple nonlinear dynamic system like that, and we have on the right-hand side, we have a function t or function of something very strange, nonlinear anyway. Okay, nonlinear, and then by using the bridge that we just described previously, and we can find the solution that we need. The idea would be the same as what we have described, and saying inside of the tiny time interval, we may find a linear system, and we solve that linear system, and then combining all those systems together, then we find the solution. Okay, indeed, and for numerical solution, we always need to find the recurrence relationship and in the time interval, and we know on the left-hand side, we have a value given, and then put them into it, and we can find the solution for next point, right, in the time interval. If that's so this, and we can find the solutions for linear and nonlinear systems. As I said, many of the linear systems that we can find the complete solution. Let's say, well, this is an example, and I have seen a linear system, or I found a solution for linear system by using the approach that I just described, and we call it PT method. That's our method, PT method. P stands for piecewise linear, and T stands for Taylor's extension. Okay, let's say, well, this one, the PT solution gives you everything is the same. And except that this part is a squared minus b over 2 minus 2c squared. And exact solution would be a squared minus b minus 2c squared. Everything's the same, except that this one is very small. And also, p minus nt over t and over nt over n is a value smaller than 1. Let's say 0.1. And to the power of 4, 0.0001. Okay, that's very small. So in other words, the PT method gives you a solution, although that's an approximate, once again, and the numerical solution is approximate solution. It's not analytical, not a complete solution. So the accuracy of the solution of a PT method is very high. Okay, let's see how high it is. As I said, Runge-Kutta method is one of the, if not the most popular method, numerical method. And we compare PT method with the Runge-Kutta method and see the error. Okay, the error. This guy, the purple square represented the error of PT method. And for the system, and this yellow triangle representing the error of Runge-Kutta method. But errors are very small. You can see 0.008, 0.008, very small. However, in comparing with the two errors, and they generated by two systems, and PT method gives you a much higher accuracy method solution with a higher accuracy in comparing with the Runge-Kutta method, which is the most popular one. Okay, which is good. We're excited about it. And however, that's a linear system though, and you know the solution. What if we don't know the solution for nonlinear system? Let's have a look. Say we use the PT method, we use the bridge, everything the same. And for the nonlinear system like that, and by using the Runge-Kutta method, we do the comparison. Comparison would be a little bit difficult if you don't know the solution. But we can say when we have the time interval selected for numerical solution very small, and the accuracy of the solution would be higher. That's commonly accepted. Okay, so but if you have a smaller time interval for calculation, then your calculation time would be longer. Right? That's the cost. So let's do the comparison. See, this one, the purple one, the line seems continuous. And the dotted line is calculated by Runge-Kutta method with a very small time interval, which is 0.003. And this yellow triangle is the numerical solution of Runge-Kutta method with a much larger time interval, which is 0.3. That's 100 times larger. So as you can see, well, the two solutions are totally different. First thing is that Runge-Kutta method gives you discrete solution. They're not continuous. Okay. Secondly, and when we increase the accuracy, the requirement of accuracy, then you needed to have a smaller time interval. However, if we use the PT method, there's another line there, okay? They're overlapped with this purple. And the solution of a PT method is about the same as the solution of the smaller time interval of Runge-Kutta method. But for PT method, we use very large time interval, 0.3. That implies we use much less time of a calculation. And we got almost the same solution as that of a Runge-Kutta method of 100 times smaller time interval. Can you understand that? Okay, so that means the PT method, solution for PT methods is very accurate and reliable, okay? Although it requires less calculation time, okay? And reliability of PT method is very important because if you use the Runge-Kutta method, you may probably not get the right solution in some case, but PT method may probably avoid that kind of disadvantage. So PT method and the Runge-Kutta method, in comparing with that, obviously PT method is much better. Okay, so that's part of our research, and we are excited about the results, and which are pretty good, and a lot of people are using it. And but as I said, there are still a lot of work need to do, and we are not really we do not really fully understand the phenomenon of a nonlinear system, why chaos happened. We know chaos happened, but why it happened? What is the mechanism of nonlinear system, and what is the cause of the chaos? And in what kind of situation that the chaos may happen? We are in lack of an accurate and reliable analytical solution there. So people are working on it. We are working on it. It's a very interesting area. Actually, as we have discussed previously, our world is nonlinear. So we have to find some way to solve for those nonlinear systems. Okay, so that's some of our papers published. If you are interested in, you can find those papers online. And you can find the titles of the papers from my website. There are many of them. And this book describes all what I have discussed today. And you can find out the physical book, in our library. And fortunately, our library purchased the electronic version of this textbook. And you can download the probably two or three chapters each student. You're allowed to download. If you want to download what I have said today, the contents, and you can download chapter 4 and chapter 5 of this book. And if you are really interested in this nonlinear system, the solution of nonlinear systems, and the application of those concepts, you can find another book of mine, and we have the applications in it. And hopefully that you will like it. And the research is obviously plays a great and important role at our university and at all the universities. And if you are interested in this topic, and or you would like to do research along this line, please contact me. Okay, that's all for what I need to say. And please enjoy the study and research at the University of Regina. That's all for today. Thank you very much. And let's stop here. See you.